Okay, so welcome back, everybody. So at the end of class last time, I had stated Stokes Theorem. So to bring that back for a second, there it is. So let sigma be an oriented surface with normal in and finite surface area. Assume sigma is bounded by a piecewise smooth closed curve C. So this is not just any surface. It's a surface that has a boundary. This boundary is going to be at least a piecewise smooth closed curve. And the orientation on this curve is going to be the one induced from sigma. So sigma needs to be oriented. That I stressed the importance of that previously. And that orientation induces, in the way that I talked about in last lecture, an orientation on the boundary curve sigma. So if that's the situation that you're in, if you take F to be a continuous vector field on sigma, that also includes the boundary of sigma. And assume the component functions of F have continuous partial derivatives at each non-boundary point of sigma, then the line integral of that vector field along the boundary curve is equal to the surface integral of the curl of that vector field along the surface sigma. So I'm going to draw a picture really quick. So this is kind of the situation you're in. So imagine that you have, here, I'm going to draw this like paraboloid looking thing here because this is actually kind of what we discussed last time. So imagine you have surface kind of looks like that. All right, so here's sigma. All right, so maybe I should have used a different color here for the boundary. So there's sigma. Here's in different color. Here is the boundary of sigma. All right, so sigma is this surface here. Here's its boundary. So the boundary of sigma is this nice smooth curve C. Sigma is oriented in such a way. So I'm not saying that sigma is always oriented such that the normal is pointing up or outward. Okay, but the orientation on sigma is taken to be such that, say, it looks like this. So in this case, if we have normal pointing, I know that perspective can be a little hard with these things. So the idea here is this normal is pointing out. So we're on the front face here. And this normal is pointing out and up in this direction. All right, so to take my fingers, I draw a little circle indicating with my right hand the orientation, so it's going that way. But what I need to do is I need to pay attention to what direction this is going nearest the boundary. So it's going around this way, so that nearest the boundary, this is indicating this is my direction. So that's on the front, and on the back it looks like that. All right, so around like that. Okay. So if this is the picture that I'm in, then I'm in exactly the situation where I can use Stokes Theorem. And Stokes Theorem would say that if I have some vector field F that is nice on all of sigma, including the boundary, then the line integral over the boundary of sigma, this boundary curve, can be computed as the surface integral over sigma of the curl of that vector field, which is itself a vector field. Right, so it's curl F dot nds, where this is just the notation that we use to denote surface integrals. Okay, so that's just a restatement of Stokes' theorem. Now, I mentioned at the end of class last time how this conforms to exactly that same form of mega Stokes' theorem, that integral over boundary of F is equal to integral over the space of df, or del F. Okay, where here our del F is the curl. Okay, so for Green's theorem, the del F was this weird, expression where I took x and y partials and subtracted them, right? So it wasn't a curl. It was this weird expression involving partials. And we're going to see one more named theorem that has that same form. The fundamental theorem of line integrals also kind of has that form as well. So anyway, where the del in that case is the gradient. All right, so anyway, how are we going to use this? So how are we going to use this? Well, the thing is that if you look at this, you might say, and this is totally correct to say this, if you know the curl of the vector field, right? And you know the vector field that it came from, then you could go in either direction. You can go forward or backward here, we'll say. What I mean by that is you can use Stokes' theorem to compute a line integral as a surface integral, or you could use this to compute a surface integral as a line integral. Now, because doing it in that direction, computing surface integral as something else, as line integral, because there's this curl here underneath, that it's not necessarily that convenient to do it that way. Okay, and so the way that we are typically going to use Stokes' theorem is to compute a line integral as a surface integral. Okay, so conceptually that might be a little strange because you saw that surface integrals are actually, like a more complicated object typically than a line integral, right? So surface integrals tend to be a little worse than line integrals because the surface integral was a generalized double integral, right? And we saw that if we were lucky in the plane, we could compute a line integral as a double integral. But this is a harder thing, right? In fact, here's an aside. Stokes' theorem in this way implies Green's theorem. Okay, so why does Stokes' theorem imply Green's theorem? If you take your sigma to be a piece of the xy plane, say bounded inside some curve C, okay, that will take oriented counterclockwise, which means I'm taking my normal there pointed upward, okay, then Stokes' theorem actually can be used to prove Green's theorem. Okay, so Green's theorem is actually hiding inside Stokes' theorem. So this is actually a generalized version of Green's theorem. That shouldn't be surprising since I said that all these named theorems that I'm going to mention are actually versions of something called Stokes' theorem. What I've been calling Mega Stokes' theorem. So anyway, so that's not super duper surprising, but it is a little weird that we would use this to compute a line integral using a surface integral when you're like, well, but a surface integral typically is worse. That's true, but in some instances it's not worse, okay, than a line integral. That's when the surface is really, really particularly simple, or the curve in question is nasty or at least inconvenient. So let's see an example of how we would do this. So here's an example. Let's take a surface in space that is part of a plane. Okay, so let's consider the plane in space z is equal to y over 2. So this is a plane in space. Okay, so z is equal to y over 2 is a plane. What does this plane look like? So let's look at the triangular piece of this plane in the first octant, bounded between these curves that I'm going to draw here. Okay, so I'm going to look at this triangular piece. It is a plane kind of cutting obliquely like this. So let's take this triangular piece where it looks kind of like that. Okay, this is my triangular piece. I didn't do a very good job drawing a triangle there. Here, maybe let's draw a different picture. I don't like that. Let's redraw this. Okay. So our plane is z is equal to y over 2. And maybe I'll get a straight edge so that I actually don't make it look too ugly. So let's pick a triangular piece of this plane. I'm going to draw it like this. I don't know why I ended up drawing this. I don't like that either. Hold on. No, let me make this a little bit longer, or make this a little bit steeper so that it looks decent. Okay. we'll get it this time. We'll just be happy with whatever I draw. Okay. So z is equal to y over 2. This is a plane. But in particular, I'm interested in a piece of this plane. And so I don't like that because it's in line with the stupid axis. That's no good. Okay, we won't be happy with what I drew. And drawing planes is not fun. Okay. All right, one last attempt. Okay, so there, we are going to be happy with this triangular piece regardless of what happens. Okay, so here is my piece of the plane z is equal to y over 2. Okay, this is plane in space. All right. And so, if this is piece of plane in space bounded between these curves, as this thing is intersecting the first octant, okay, so I'm going to have curves. So here's my sigma. It's the piece of this plane, and it casts a shadow, of course, over the xy plane. It looks something like that. There's the shadow that it casts. Maybe I'll use in red here to indicate the shadow cast by that piece. So what is this line in the xy plane? This line bounding the region is the line x plus y is equal to 2. Okay, so this is my R here, bounded. Okay, this is my region, the xy plane, that is the shadow of this sigma. And so sigma is taken to be this surface with orientation pointing up. So sigma is that triangular piece. Maybe I should shade that a little bit to show you what sigma is. So there's my sigma. Okay, this little shaded piece, that's my sigma. Okay. Okay. So this is a surface with boundary. What is the boundary? Well, the boundary consists of 3 parts. There's this curve. So I'll outline in black. I don't know if you can see that. So that's C1. And there's this curve. That's C2. And lastly, there's this last piece, which is C3. And so the boundary of sigma consists of curves C1, C2, and C3. It's like the concatenation of those curves. Concatenation just means you follow one curve and then the next curve starts where that one ends, and so on. Okay. All right. And so if I have picked the orientation on sigma with the normal pointing up, what orientation does that induce on this boundary curve? Well, it's easy to see in this case because this is this triangular piecewise smooth curve kind of looks like this. It's doing this. It's easy to see that, oh, like my right hand fingers are curling this way. So the orientation looks like this, right? The arrows are like that. So if I view it from the top, right, if my eyes are up here looking down, then this is counterclockwise rotation. Okay, so that's what it looks like. Okay, so that's my sigma. Now we have a drawing that we can somewhat understand. That's what my sigma looks like. All right, so say that C is that oriented triangle. So C is the oriented triangle drawn here. Now, of course, theoretically, I could actually figure out exactly how to parameterize all of those, but I'm not going to do that. So first, I'm going to ask if f of xyz is the vector field minus 3y squared I plus 4zj plus 6xk. Okay. Calculate the line integral over C of that vector field. So this is the quantity I want to compute. Notice I didn't say anything about using Stokes theorem. I just asked to compute a line integral along this curve in space. Why would I think to use Stokes theorem? Okay. Well, look at what I would have to do if I didn't use Stokes theorem, right? So if I didn't use Stokes theorem at all, what I'd have to do is, since I'm doing the line integral over the C, if I was just going to do this the brute force way, and you should know how to do a line integral the brute force way. That's something that you might have to do on the final exam. But if I was going to do a line integral the brute force way, I would have to look at this curve C, which is composed of these three curves, right? So it's a piecewise smooth curve composed of these smooth parts that are just linear, C1, C2, and C3. I would have to find a parametrization for each of C1, C2, and C3. All right. Once I found that, I would have to compute this line integral in the way that I suggested you could do, which is you just split it up, right? So you would be the line integral, you would do the line integral over C1 of f dot dr plus the line integral over C2 of f dot dr plus the line integral over C3 of f dot dr. Now, you could absolutely do that. There's nothing stopping you from doing it that way, but this is really inconvenient. Okay, I would basically be doing this line integral as three separate line integrals. Some of the results, this would be really nasty. It'd be too much work to do it this way. And so the idea is to use Stokes theorem. So idea is use Stokes. Right? So use Stokes theorem. And the reason that we can do that is in this situation, we are in the exact situation to say, oh, I could actually compute this line integral as the surface integral over this surface, where this surface is part of a plane. This is a pretty easy surface to deal with, of the curl of that vector field, right? Dotted with n ds. And remember, this is just notation, so this is to compute a surface integral. Once I've computed the curl, then now I'm in the case of just computing a surface integral like I've done previously. Okay. So what do I want to do here? So first I want to compute the curl of f. So here is my f. Let's compute the curl real quick. So what is curl of f? Okay, so remember notation for curl. So physicists, write curl maybe as like gradient cross f, can help you remember how this is actually done. So if I'm treating this like a cross product, my first row is ijk. My second row are the partial xyz operators. Okay, and then now finally I have my pieces of f here. So this is minus 3y squared is in the I slot, 4z is in the j slot, and 6x is in the k slot. Okay. All right, so now I treat this as a dot product. So the thing multiplying I cross out the I column and first row. So I would have the y partial of 6x, which is 0, minus the z partial of 4z, which is 4. So that's 0 minus 4i. Minus, in the j slot, is the x partial of 6x, so that's 6. Minus the z partial of minus 3y squared, which is 0, j. Plus, in the k slot, I'm going to have the x partial of 4z, which is 0. Minus the y partial of minus 3y squared, which is minus 6y. So minus 6y. Okay. And so simplifying this is minus 4i minus 6j plus 6y. Okay. Right. Now, this is a particularly nice curl. Typically, the curl will be a vector field involving x, y, and z, right? But in this case, it only depends on y, and only one slot does. Okay. All right. Now, we're ready to use Stokes Theorem to say my line integral of f, this vector field over that boundary curve C, is equal to the surface integral over that triangular piece of that plane, sigma, of curl f, which I just computed. But remember, how do I do surface integral? What are the things I need? Okay, so I have curl f, so I'm good to go. But in order to actually compute the surface integral, I need to describe sigma as a parametrization, right? So I need to describe it as parametrization. So let's recall, what is sigma? Sigma is a piece of the plane z equals y over 2. Okay, so it's a piece of that plane in the first octant. Okay, which really means it's this triangular piece. So if I think of x and y being my parameters describing where I am, the height is described by z as y over 2. And this region R that my parameters x and y live in is the shaded region that I drew here. So it's the region in the first quadrant of the xy plane that is, below the line x plus y is equal to 2. Okay, but in the first quadrant. So how do I deal with that? Well, this is a plane, but really this is a graph of a function, right? So this is the graph of a function f of xy, where f of xy here is y over 2. Okay, and so how do I parameterize this? Well, it has a simple parameterization, right? So I can use that trick that I always do. If my sigma is actually the graph of a function, then the parameterization is xi plus yj plus f of xy k. Okay. Now, I've actually already computed what the x and y partials of this parameterization are. In general, I did that last time. So if you're confused by the next step, you can have a look at last lecture. So this is for x and y living in R, where R is this region in the xy plane. Right, where here, this is the line x plus y is equal to 2. Right. Okay, so there's my region R. Well, how do I describe that region? Well, so x plus y is equal to 2. That is the line y equals 2 minus x. Okay, and 2 minus x is described as, in terms of x, going from 0 to 2. Right, and so R is a vertically and horizontally simple region. But of course, we'll just describe it as a vertically simple region. So y is bounded below by constant function 0 and above by the line 2 minus x. And x is bounded between 0 and 2. Okay, so there's my description, this parameterization. To do surface integral stuff, I need to compute this, right, typically. So I would find the x partial of this, find the y partial of this. I would cross them, and I would get something. Does anyone remember what I get in this case, right? So if my parameterization was not this simple, if the surface I was using was not the graph of a function, if it was like a sphere, right? Instead, then the parameterization would be more complicated, and I would have to actually compute this by hand. But here we've actually already computed this thing. So when we compute like this, what do we find? Right, so what is the thing that we found? So we actually found that this was, in the case of a parameterization that looks like this, we computed last time that this was always minus, right, f sub xi minus f sub yj plus 1k. All right, and you can just verify that this is how it works. So in the event that our parameterization is given by graph of function, we always know this. But you got to be careful here. If it's not in exactly this form, this isn't going to be true. You're going to have to compute this by hand. Okay, and when we compute this, we will check that this actually points, the normal points in the same direction. So let's do that here. So in this case, what is my parametrization written out explicitly here? Well, rewriting this is the parameterization xi plus yj plus my function f of xy is y over 2. Right, okay. And so this r sub x cross r sub y is minus the x partial of f. Well, that's 0, I. Minus the y partial of f, which is minus 1/2, okay, j, plus 1, k. All right. Okay, what direction does this normal point in? Well, this last component is positive here. This is the normal pointing up. It's pointing off to the left here. That's what's indicated by this minus 1/2, but it's pointing up. Okay, it's pointing up. The reason for that is because basically the implicit orientation here that we're assuming whenever we parameterize the graph of a function to variables like this is the one with the normal pointing up. Okay, and that happens to be the same one we're using here. Okay, if this was the opposite orientation, then we would have to introduce a minus sign coming up. Okay, so then I want to compute this thing. So I'm not going to rewrite that. I'm going to come down here. How do I compute that thing? Using the definition of surface integral. This is going to be the integral from 0 to 2, the integral from 0 to 2 minus x, of what? Of the curl of f, which we computed previously, is this thing. So there's the curl. So it is going to be curl of f dotted with this normal that we found. And so it's going to be minus 4, right, dotted with, and of course, let's pay attention here, right? So normally, what I would be doing is I would be plugging in the parametrization here for any x, y, and z that show up. Okay, but the only x, y, or z that shows up is here, right? And what do I plug in, coming from the parameterization, for y? Well, y. Y gets plugged in for y. So it doesn't look like anything's happening here. This is why a lot of these early examples in Stokes Theorem are a little confusing, because it doesn't look like you're doing anything extra here. Okay, but you're technically plugging in y for y. If in this parameterization, this expression was y squared z, then here in this curl, what gets plugged in here is y squared z. So this last slot, when I put it underneath the integral sign, would be 6y squared z. Okay, for instance. All right, but in this case, we don't really have to do much of anything. So this is minus 4 times, I'm dotting this with r sub x cross r sub y. So this is minus 4 times 0 plus minus 6 times minus 1/2. Okay. Plus, yeah, right. So I've already put the minus 1. Yeah, that's fine. Plus 1 dotted with 6y. So this is 6y times 1. Again, I'm actually plugging in for y here. Okay, dy dx. Okay, so simplifying what I get here, this is the integral from 0 to 2, the integral from 0 to 2 minus x. Nope, not 2x, x. What is that? 2 minus x. Okay, well, this is 3, and this is 6y, and that's 0, so this is 3 plus 6y, dy dx. Okay, well, that's not so bad here. I can actually factor out a 3 if you like. So this is 3 times the integral from 0 to 2. What's left behind is 1 plus 2y. What is the y integral of that? So this would be y plus y squared, right? And that's evaluated from 0 to 2 minus x dx. Okay. So if we plug this in, what do we get? We have 3 times the integral from 0 to 2 of 2 minus x plus 2 minus x all squared. So if I factor out a 2 minus x there, that would be, that would be 2 minus x times 1 plus 2 minus x. Right, so it would be 3 minus x here. And so we really just need to expand this thing. Okay, so expanding this thing, I would have 6 minus 5x plus x squared dx. Okay. And so evaluating this integral, this would be 3 times 6x minus 5 halves x squared plus 1/3 x cubed, evaluated from 0 to 2. So evaluating at 0, I get 0, so I really just need to plug in 2 here, so let's do that. So here, I would get 12 minus 5 halves times 4, so that's 12 minus 10, right, so that's 2, okay, plus 8 thirds. So 3 times 2 plus 8 thirds would be 6 plus 8, so 14. Okay. All right. So there's our surface integral. All right. And so what did we actually do? We computed this line integral, and we did it in a way that we didn't have to break it up. Right? We were able to just do it in one go. All right. So there's an example of using Stokes theorem in this way. So I will talk about some other examples of using Stokes theorem. Some other specific examples, but I might do that in the review session on Monday. So I'm going to conceptually mention something that you can do here that's pretty funny, which is using Stokes theorem when you have two surfaces that are joined along an edge. So let's say we have two surfaces, say sigma 1 and sigma 2, joined along an edge to form a bigger surface that we'll just call sigma. So what's an easy way to come up with an example of this? What if we again have this paraboloid thing where the top of the paraboloid is sigma 1, and instead of this thing being open, okay, so instead of this thing being open at the bottom, imagine you've put like a cap on it. So it has a bottom that is actually solid that you can, sit it down on something. We'll take that to be sigma 2. All right, and so they are joined along a curve. All right, so they have a shared boundary, C. So the boundary of sigma 1 is C, and the boundary of sigma 2 is C. Okay. So they are bounded by the same curve. Now, there's two options here. Okay. So there's two options. So let's do case 1. Sigma 1 and sigma 2 induce the same orientation on the boundary curve. What happens in that case? All right. Well, in that case, what might that look like, right? What would you have to do? So let's say the orientation we take on sigma 1 is this one, up and out, right? Here's my normals, up and out. That would induce what kind of orientation on the boundary curve C? Well, one that looked like this. So on the back, it would look like that, and on the front, looks like this. Okay, that's my orientation on C. What orientation for sigma 2 would I have to pick that induced that same orientation? Well, this one. Right? That would do it. So if these are the two orientations on sigma 1 and sigma 2 respectively, they would induce the same orientation on the boundary curve C. But then what does Stokes' theorem tell you? So then by Stokes, what do we have? Well, we have that the surface integral along sigma 1 of the curl of vector field f dot n ds. By Stokes' theorem, this is equal to, of course, the line integral over the boundary curve C of that vector field f. But then also by Stokes' theorem again, this integral, this line integral, has to be the same as the surface integral over sigma 2 of the curl of f dot n ds. So we're assuming that f and curl of f are defined on sigma 1, sigma 2. Okay. And nice. Nice, defined, and continuous. Okay. Now, of course, you might say, wait, the ends here are technically different, right? So my normals here are determined by some normal assigning thing, we'll call it n sub 1, and my normals down here are determined by some normal defining thing called n sub 2, and that's true. So technically, right, we have two different ways of assigning the normal there, so we should be careful, and we can list this like this, but this is the idea. So these two integrals, so integrating the curl of f over sigma 1 is the same as doing the surface integral of curl of f over sigma 2 in this case. All right. Now let's think what happens in case 2, which is instead of they induce the same orientation on C, let's say they induce the opposite orientation. So sigma 1 and sigma 2 induce the opposite orientation on their boundary curves, their shared boundary. Well, what would this picture look like? Take the exact same picture, but instead of taking your normals pointing up, take them, say, pointing down here. Okay. What would that indicate? That would indicate that the surface integral of curl of f dot, so n1 ds is equal to minus the surface integral of sigma 2 of curl of f dot n sub 2 ds. Where does this minus sign come from? Well, as before, we have to go through this line integral, right? Where does the minus sign come in? Because in one application of Stokes, we get C, and in the other application of Stokes, we get minus C because the orientation in question induces the opposite orientation on the boundary curve. Okay. And so in this case, we have minus. Okay, we have minus minus the surface integral along the other surface is equal to this thing. So what is an application of this? Quick application. So here's homework, we'll say. Okay, this is not including any homework. I just want you to do this to check that you understand what's going on. Let sigma be the unit sphere. So unit sphere is x squared plus y squared plus z squared is equal to 1. Okay, oriented with normal directed outward. Okay, let f be any vector field any vector field whose component functions have continuous partial derivatives on sigma with continuous partials of the components on sigma. Show that the surface integral along the sphere of the curl of such a vector field is equal to 0. Okay. So my hint in how you can do this is that last conceptual bit that I was talking about, having two surfaces that have a shared boundary curve. Use that. Okay, so use that. Split the sphere into two surfaces that share a boundary curve. There's an obvious way to do this. Okay, and use those two facts that I stated before, or one of those two facts, to show that this always has to be 0. It doesn't matter what f is. Okay, doesn't matter what f is. Okay, this always has to be 0. Okay, so physically this has this has an implication, but I won't say anything else here. Okay, now we are on to the last topic, which is the divergence theorem. Okay. So what is the divergence theorem? So even though the divergence theorem is the very last named theorem we cover, it's actually significantly easier than Stokes' theorem because the idea behind the divergence theorem is to get around computing a surface integral, which is nasty, via an integral which is not so nasty. Okay. So what is the setup in the divergence theorem? Let D be a simple. This is simple in the same way that the regions D that we did triple integrals on were called simple. So those same exact regions D that we were triple integrating on, we called those simple, and those are the only ones we did. Okay, so let D be a simple solid region in space. So a simple solid region whose boundary is a surface sigma. Okay. Oriented with normal directed outward. Okay. That is outward from D. And that's our perspective. And let F be a vector field whose component functions have continuous partial derivatives on D. Have continuous partials on D. Then, first of all, let's draw a picture of this real quick. What would this look like? So I have some, say, 3D ball. So that's the ball and everything inside of it. And there's a boundary surface, right? So I have the ball and everything inside of it. Maybe I'll shade it like this to indicate that includes everything inside. Okay. So that's my D. But then I have the outside of the ball, right? Just the surface, right? The boundary surface of the ball. So the boundary of D is a surface sigma. In this case, it looks like a sphere or maybe a slightly deformed sphere. Okay. And we have this set up in such a way that the orientation on D is taken such that it induces an orientation on the boundary surface of pointing outward. Okay. All right. Then, suppose I want to integrate the vector field F along that boundary surface. I can compute this as the triple integral over the region, the entire region, of the divergence of the vector field, which is a scalar valued thing. You already know how to triple integrate such things. So boom, there it is. Okay. And now you see why the divergence theorem is actually easier to apply, because how are we going to be using this, right? We are never going to be using this to go backwards, right? We're never going to be using this to compute a triple integral as a surface integral, because computing triple integrals are typically easier, right? So we're not really going to be using this to go backwards, typically. We're going to use it to go forwards. And going forwards, we are avoiding computing a surface integral by computing a triple integral. Okay? And computing triple integral is something we know how to do. So let's just do an immediate example of the divergence theorem. Most of the examples of the divergence theorem that you see are actually going to be very simple to do because, well, it's an easy thing to apply. So let's do a quick example. Suppose sigma is the sphere of radius 2 centered at the origin. So we'll say it's the sphere x squared plus y squared plus z squared is equal to 4. And F is the vector field x, y, z given by 3xi plus 4yj plus 5zk. And let's evaluate the surface integral over that surface sigma of my vector field F. Now, how would I do this? Again, note, I do not say apply the divergence theorem, even though that is exactly what we're going to do. I don't say that, right? I just ask you to compute surface integral. So on an exam, right, you might not even see the words Stokes theorem, divergence theorem, Green's theorem. You might not see any of those words. Okay. So if you don't see any of those words, how would you know to use them? The idea is you have these named theorems. You should know in what context they apply, and you should just think about how much work you might have to do if you did it without using them. So how much work would I have to do if I was doing a surface integral like this? I would have to write out the parameterization. Now it's a sphere, so I could use spherical coordinates to come up with that parameterization pretty easily. But I come up with that parameterization. I compute, r sub theta and r sub, r sub theta and r sub phi, right? And I cross those. And of course, maybe you just remember the form that takes, so you're lucky here that it's a sphere. But still, that's some extra computation you got to do. And then once you've done that, you have to plug the parameterization in spherical coordinates into vector field F, right? And dot it with that r sub phi cross r sub theta that you found. And then you would do that double integral that results, right? Which may or may not be pretty nasty. But how can I do this with the divergence theorem? So how can I do this with the divergence theorem? Well, note that if sigma is the sphere, right, then D, the inside of the sphere, such that the boundary of D is sigma, D is the solid ball of radius 2. Okay. All right. So what do I do here? Well, note that the divergence of this vector field F is the x partial of the x partial, which is 3, plus the y partial of the y partial, which is 4, plus the z partial of the z partial, the z partial of the z slot, which is 5. Just to say that again. The divergence of the vector field is the x partial of the x slot, which is the x partial of 3x, which is 3, plus the y partial of the y slot, which is 4, plus the z partial of the z slot, which is 5. So this is 12. So the divergence of f is actually just a constant. And thus, by divergence theorem, this surface integral can be computed as the triple integral over d of 12, or I'll write it as divergence first to actually write it as divergence theorem. Okay, so this is triple integral over d of 12, right? So it's triple integral over d of 12 dv. So this is 12 times the triple integral over d of 1 dv. What is that? What is that? This is the volume of a sphere of radius 2. All right, so this is volume of sphere of radius 2. Now you better know how to compute that. Archimedes would be sad, right? So Archimedes would be very sad if he knew that you didn't know how to compute the volume of a sphere with a given radius some 2,200 years later. All right, so this is 4/3 pi r cubed, right? So this is 12 times 4/3 pi r cubed. R here is 2. So it's 4/3 pi times 2 cubed. So that is divided by 3. So it's 16 pi times 8. So that's 128 pi. Now, going to ask, was that easier than computing a surface integral? Well, yeah. Allison, so we would use the theorems more as tools. They aren't required. Yeah, so that's most of these problems are going to be stated in a way that basically makes it so that you don't necessarily have to use them, but they'll make your life a lot easier. So if you go to try to do a brute force line integral or a brute force surface integral and you see that you feel like it's just too nasty, right? Then you might think about trying something else, okay? Now, it's possible that sometimes there is nothing else. Sometimes you're kind of forced into doing something that's maybe not so nice, but it's at least nice to have these in the back of your head as other options to try if you're stuck on something, or if you think something's a little bit too nasty. Okay. All right. So that is that. That is all the course material. So on Monday, bring questions you have about the course material, and I will answer them. Monday's lecture is going to be a review session. So any questions you have, remember, final exam is cumulative, so you can ask me questions about whatever. I will default, if no one has that many questions, I will default to just doing some examples so more examples of Stokes Theorem, more examples of Divergence Theorem stuff. That's what I will default to doing in the absence of questions, but otherwise I will just spend the whole time answering questions. So bring questions, all right? Okay. All right, so I will see you all Monday then. I posted an announcement overnight that cleared up what's going on with the final exam. So final exam is going to be posted on the first day of finals, which is 13th. Next week, it'll be posted by 1:30 p.m., which is your official final exam time that it's scheduled. But it's not going to be scheduled or anything. It's going to be just like all the other exams, so you'll have 2 days to do it, and that will be that. And that will be the end of the course. So remember, you have a couple other assignments. Your second MATLAB and homework 6 are due next week as well. So anyway, and then that will be that. So when you submit your final exam, you will be done with the course, and your grades will be posted a few days later. So anyway, I will see you all on Monday.